Yes. So last classes we discussed about bending stress, tensile bending stress, compressive bending stress. So we derived the pure bending equation or simple bending equation. M by I is equal to F by Y is equal to E by R. Then we discussed about moment of resistance of a section or moment carrying capacity of a section or modulus of rupture. So all the three same. And section modulus Z. How to find section modulus, all those things we discussed. Then we did some problems on I section, T section, rectangular section, like that, finding the load that can be carried given the permissible stress, or finding the bending stress at the extreme fiber, plotting of bending stress diagram. So bending stress diagram will be a straight line. So on that day I told about that. Now today we will discuss about shear stress distribution. So this is another part. So whenever a beam is subjected to some external load, both bending moment as well as shear force will develop. So that we have discussed in the last chapter, BMD and SFD chapter. So simultaneously they will be there. So only thing is, if shear force is zero and bending moment is constant, then it is called as pure bending. But not always that is possible. Only in some examples you can have that pure bending case. Now let us see how we can get the expression for shear stress at any section in a beam. So shear stress is. So shear force irutte. So how that shear force will be having the effect on the shear stress. So one thing you should keep it in mind. Shear force is an external effect. Shear stress is an internal effect. So bending moment is an external effect. Moment of resistance or modulus of rupture is an internal effect. So they should be equal for equilibrium. Or whatever that is internal resistance is there, if it is greater than the external effect, then it will be safe. At the most, it should be equal. Suppose if the internal resistance is less than the external load or moment, whatever it is, then the material will fail. That is the thing. Okay. Now let us see how shear stress expression can be derived. So this is another important derivation. So ಎರಡು derivation. So ಒಂದು pure bending equation, another one is shear stress derivation. So shear stress derivation ಗೆ ನೋಡಿ ನೀಟ್ ಆಗಿದೆ, sketch observe ಮಾಡಿ ಇಲ್ಲಿ. So this book I have sent you, Mechanics of Solids by Bobby. So same book I am referring. See here, this is a portion of a beam. It is beam. So I am taking an elemental length AB. AB is an elemental length of a beam. And this is the cross section. So cross section, he has taken an irregular cross section. So this cross section of the beam can be anything: rectangle, circular, triangle, square, I section, T section, yav bekaro agbodu. So that's why he has taken an arbitrary cross section of the beam. And here he has given one more sketch. See, this is along the perpendicular to the board in this direction. That means by taking CD as the elemental length. So in CD he has taken as an elemental strip. We can call it as elemental strip. CD is an elemental strip which is taken in the elemental length AB. So that elemental length is taken as delta x. Delta x is the elemental length. So the x direction represents the length of the beam. Y direction represents the depth of the beam. Y direction represents the depth of the beam. This is width of the beam. E direction is the width. So CD, C dash, D dash and so this is width of the beam. Width of the beam here, perpendicular to the board. Okay. So like that. So length of the beam is in this direction. This is thickness, that is depth of the beam, and this is width of the beam. So what I have taken an elemental strip CD at a distance y from the neutral axis. So it is neutral axis or neutral layer. So length of the beam we call it as neutral layer. Cross sectionally neutral axis. So it is neutral axis. So they are mutually perpendicular to each other. So this is the cross section. In the cross section we call it as neutral axis. In the longitudinal section, this is called as longitudinal section, we call it as neutral layer. So where the stress is 0. So bending stress 0 irutte ಇಲ್ಲಿ ಆಯ್ತಾ, but shear stress 0 ಇರುವುದಿಲ್ಲ. That's what we are going to prove now. So bending stress is 0 along the neutral axis. ಈ axis ಅಲ್ಲಿ bending stress 0 ಇರುತ್ತೆ. YT ಅಂದ್ರೆ distance of the top fiber. T stands for top. So distance of the top fiber from the neutral axis. ಆಯ್ತಾ, ಮತ್ತೆ ಇಲ್ಲಿ CD length of CD is delta x. Length of CD is delta x. Width of CD, width ಇರುತ್ತದಲ್ಲ, so ಇದು cross section width ಹೀಗಿರ್ತದೆ. So width of CD I am going to take it as B. B is the width of CD. So distance of this CD from the neutral layer or from the neutral axis is y. ಈ ಡಿಸ್ಟೆನ್ಸ್ ಇದೆಯಲ್ಲ, ಇದು y. Thickness of CD I am taking delta y. ನೋಡಿ, ಇದು ಅರ್ಥ ಮಾಡ್ಕೋಬೇಕು. So these are the dimensions. Delta x is the length of this elemental strip CD. B is the width of CD. YT is the distance of the top fiber from the neutral axis. Y is the distance of the elemental strip CD from the neutral axis. Delta y is the thickness of the elemental strip. And M is the bending moment here. So the bending moment at A is M. The bending moment at B is M plus delta M. So because the bending moment varies from point to point, I will take the bending moment here at B as M plus delta M. At A it is M. So just to say that the bending moment differs over this length. That is the meaning. So ಎರಡು sagging ತಗೊಂಡಿದ್ದೀನಿ. So this is sagging. So if you take like this, bending moment is sagging bending moment. So according to our sign convention, sagging bending moment is positive. So that's what has been explained here. Consider an elemental length delta x of beam shown in the figure. Let bending moment at section AA be M and at that section BB be M plus delta M. Let CD be an elemental fiber. This is the elemental fiber at distance y from neutral axis and its thickness is delta y. That's what I told. Now let us see how the derivation starts. So now we know that according to our bending equation, M by I is equal to F by Y. So F andre bending stress. So that is F is equal to M by I into Y anta. So F andre eno bending stress on left side of elemental fiber. Left side of the elemental fiber. CD is the elemental fiber. Left side of elemental fiber means C. C is the left side. So M is the bending moment. So here F at the left, F at C is actually. So we can write it as FC anta ಕರಿಬಹುದು ನಾವು ಇದನ್ನ. So bending stress is given by M by into Y. So ಇಲ್ಲಿ moment M ಇದೆ. So M divided by I is the moment of inertia of this cross section. So by knowing the cross section, rectangle, triangle ಯಾವ್ದಿರುತ್ತೆ ಅದು, we can find out that moment of inertia into Y is the distance from the neutral axis. So this is what so the bending equation is. So M by I is equal to F by Y means F is equal to M by I into Y. ಅದನ್ನ ಬರೆದಿದ್ದೀನಿ ಇಲ್ಲಿ. Similarly, what is the bending? You can calculate the force. ಇದು stress ಆಯ್ತು ಇದು. So F is equal to M by I into Y is the stress. To convert that stress into force, you have to multiply it by the area because stress is force divided by area. So ಇವಾಗ ಏನಾಗ್ತದೆ? Now let us see how do you calculate force then. Force on left side of the element. So we are calculating left side. Left side is C here. So ಇಲ್ಲಿ stress M by I into Y ಇದೆ. When that stress is multiplied by the area, so area ಅಂದ್ರೆ ಈ ಏರಿಯಾ ತಗೊಳ್ಬೇಕು. Area you can see here. ಇದು cross section ಇದು. Area ಏನಾಗುತ್ತೆ? Elemental strip area is B into delta Y. A rectangular area ತಗೊಳ್ಬೇಕು. Small rectangular area. So B into delta Y. So that means you are going to get the force on the left side as M by I into Y is the stress. When that stress is multiplied by B into delta Y, that is the area of that strip, you are going to get the force. So force is equal to stress into area. Similarly, ಇದೇ ತರ, what is the force on the right side of the elemental fiber? Right side ಯಾವುದು? Right side D. So what I am doing is I am writing bending stress here. I am writing bending stress here. So right side only, what is the moment? M plus delta M. So instead of M, you have the bending moment as M plus delta M. So again, I get the same expression because the area remains same. B into delta Y irutte. ಅರ್ಥ ಆಯ್ತಾ? So only thing is the difference is instead of M, you have M plus delta M. So divided by I into Y into B into dy. ಅಷ್ಟೇ. So M is replaced by M plus delta M. So this is the force on the right side. ಈಗ ಇವೆರಡಕ್ಕೂ ಡಿಫರೆನ್ಸ್ ತಗೊಳ್ಬೇಕು ನಾವು, ಬಿಕಾಸ್ this force, see, this force will be acting like this, this force will be acting like this, both are compressive. So let us assume that, let us take that this is a simply supported beam. Simply supported beam nalli above the neutral axis compression irutte, below the neutral axis you have tension. So that is why compressive force barutte. So ನೋಡಿ ಇದು m by I into y into b into d delta y, ಇದು ಇಲ್ಲಿ compressive force. So m plus delta m by I into y into b into delta y, illi compressive force. So both are compressive. So unbalanced force means the difference between these two. It is equal illa. So you have to take the difference. So what is the difference? So unbalanced horizontal force tane idu. So this is horizontal force. So unbalanced horizontal force is difference between these two. Avarna kaladaga enaagtade nodi, see, this minus this. So if you subtract, you will be left with only delta m by I. Idella it cancel agutte. One term will cancel. M by I into y into b into delta y term will get cancelled. So you will be left with delta m by I into yb into delta y. So idu ulkollutte. Like this, this is the unbalanced horizontal force on the elemental fiber. The elemental fiber alli. Iದೇ ತರ ನಿಮಗೆ whatever fibers are there above this CD, ಈ CD ಇಂದ ಮೇಲೆ ತಗೊಳ್ಬೇಕು ನೀವು. So that means between the from y to yt. So y is the distance from the neutral axis to here. Yt is the distance from the neutral axis to top fiber. T stands for top. So between y to yt, so whatever horizontal forces are there, that we have to add. ನೋಡಿ add ಅಂದ್ರೆ ಇಲ್ಲಿ integration. Please ಅರ್ಥ ಮಾಡ್ಕೊಳ್ಳಿ. There are a number of such elemental fibers above CD. Hence unbalanced horizontal force on the section CD. So ಈ CD ಮೇಲೆ ಇದ್ರ ಮೇಲೆ ಇರೋದೆಲ್ಲ ತಗೊಳ್ಬೇಕು ನಾವು. So whatever forces are there above this CD, that you have to take. If you want to take that, you have to integrate between y to yt. A force ಇದೆಯಲ್ಲ, a force expression na. So what is the unbalanced force? You have got this. This is the unbalanced force. This should be integrated between y to yt. That's what has been done here. See here. The integration y to yt delta m by I into yb into delta y. ಇಲ್ಲಿ dm delta m ಎಲ್ಲ ಒಂದೇ. So ಇಲ್ಲಿ ಪ್ರಿಂಟಿಂಗ್ ಇದಾಗಿದೆ ಅಷ್ಟೇ. So this is delta m. So you have taken it as delta m. ಇದೆಲ್ಲ delta m ಆಗ್ತದೆ. ಅರ್ಥ ಆಯ್ತಾ? So delta m. So now in this delta m can be taken outside. Only y is the variable. ಅವಾಗ ಏನಾಗ್ತದೆ ಇದು? So delta m by I into integral y into b into dy ಬರ್ತದೆ. So between the limits y to yt ಅಂತ ಅಂದ್ರೆ we are taking the sum of the horizontal forces, unbalanced horizontal forces above that layer CD. Above the layer CD ಅಂದ್ರೆ limits of integration will be from y to yt. ಈ y ಇಂದ ಇಲ್ಲಿಂದ ಇಲ್ಲಿಗೆ ತಗೊಳ್ಬೇಕು, ಅರ್ಥ ಆಯ್ತಾ? y to yt. So this is the unbalanced force due to the moment that is existing between these two points. Now this should be equated to shear force. ನೋಡಿ ಇದನ್ನ, you know the relationship between bending moment and shear force ಅಲ್ಲ? So now what we have to do is see this figure. See this figure, you see there is an unbalanced force due to this and this. So you have taken the difference. ಅದು ಹೀಗೆ ಆಗ್ತಾ ಇರ್ತದೆ because this is more m plus delta m. Let us assume that m plus delta m is positive. If delta m is positive, this is more than this. ಅವಾಗ ಏನಾಗ್ತದೆ? ಡಿಫರೆನ್ಸ್ ತಗೊಂಡಾಗ, so whatever delta m by I ಇದೇನಿದೆ, delta m by into yb delta y ಇದೆಯಲ್ಲ, that will be acting like this, and that should be resisted by a shear stress in the opposite direction. ನೋಡಿ shear stress ಇದು ಜಾಸ್ತಿ ಇರೋದ್ರಿಂದ ಇದು ಆಕ್ಷನ್, ಇದು ರಿಯಾಕ್ಷನ್. ಸೊ shear stress will be acting in the opposite direction. ಅದಕ್ಕೆ ಈ ತರ ತೋರಿಸಿದ್ದಾರೆ. Now let us write the expression for this shear stress and we will equate to that. So this is the unbalanced horizontal force above the elemental strip CD. Let intensity of shearing stress on the element CD be Q. That's what. ಅದನ್ನ Q ಅಂತ ಇಟ್ಕೊಳ್ಳಿದ್ರೆ. So this Q will be acting in the opposite direction of this. Okay? Opposite direction of this. Then equating resisting shear force to unbalanced horizontal force. So this is the unbalanced horizontal force. this should be equated to resisting shear force. Shear stress Q idre shear force ಏನಾಗುತ್ತೆ, that shear force shear stress should be multiplied by the area. ಇಲ್ಲಿ area ಯಾವ್ದು ತಗೊಳ್ಬೇಕು, area we have to take so this is acting over this length. ಈ ಲೆಂತ್ ಅಲ್ಲಿ ಆಕ್ಟ್ ಆಗ್ತಾ ಇದೆ, CD ಲೆಂತ್ ಅಲ್ಲಿ this shear force is acting ಅಂದ್ರೆ ಡೆಲ್ಟಾ ಎಕ್ಸ್, ಅದು ಲೆಂತ್ ಡೆಲ್ಟಾ ಎಕ್ಸ್, width B. So B into delta x is the area over which that Q is acting. So please note down the difference here. B into delta y is the area over which that bending effect will be there. B into delta x is the area over which shear effect will be there. So ಅದಕ್ಕೆ ಏನಾಗುತ್ತೆ ಇಲ್ಲಿ, so we have to multiply that Q by B into delta x. ನೋಡಿ ಇಲ್ಲಿ, so Q into B into delta x, this is the shear force. Q is the shear stress, B into delta x is the area. So shear stress into area gives the shear force. So Q into B into delta x is the shear force acting over that elemental strip CD, and that should be equated to this horizontal unbalanced horizontal force. Nodi equate madidare. So once it is equated, now you can just simplify this. See, delta x is taken below this side. So 1 by B into I. This B also has been taken this side. So Q is equal to delta M by delta x into 1 by B into I into integral y to yt y into B into dy. Idralli, as delta x tends to 0, so this can be written as dm by dx. Derivative ತರ ಬರೀಬಹುದು. So Q is equal to dm by dx into 1 by ei into ಇದೇನಾಗುತ್ತೆ ಗೊತ್ತಾ? So this can be written as, ಇದು according to the definition of moment of centroid definition, ಇದು ಜ್ಞಾಪಕ ಇಟ್ಕೋಬೇಕು ನೀವು, ಇದರ ಮೆಕ್ಯಾನಿಕ್ಸ್ ಅಲ್ಲಿ ಬಂದಿದೆ. So this integral y to yt b into y into dy ಇದೆಯಲ್ಲ, this can be written as a into y bar. ಇದೊಂದು ಸ್ಟೆಪ್ ಜ್ಞಾಪಕ ಇಟ್ಕೊಳ್ಳಿ. So this can be written as, this integral can be written as a into y bar, where a is the area above that CD. ಯಾವುದು ಗೊತ್ತಾ area? So ಇಲ್ಲಿ ಒಂದು another thing you should keep it in mind. A is this above this ಏನಿದೆ ಅದು area. Above this elemental strip CD ಮೇಲೆ ಏನು area ಇರುತ್ತೆ, ಇದು ಈ area. Only this much from here to here. Whatever area is there, that is your small a. And y bar is the distance of this neutral axis from the centroid of that area. ನೋಡಿ ಇದು ಏರಿಯಾ, ಇದ್ರ ಮೇಲೆ ಈ ಸ್ಟ್ರಿಪ್ ಮೇಲೆ ಏನು ಏರಿಯಾ ಇದೆ, ವಾಟ್ ಎವರ್ ಏರಿಯಾ ಇಸ್ ದೇರ್ above this strip, that area, and you have to locate the centroid of that area. So distance of the centroid of that area from the neutral axis is y bar. So that combinedly a into y bar is called as, ಅದು a into y bar term ಏನಂತ ಹೇಳ್ತಾರೆ, moment of the area above the section under consideration about the neutral axis. ನೋಡಿ ಅಂದ್ರೆ a is nothing but the area above this fiber. Suppose if you locate the centroid of this area somewhere here, distance of that centroid from the neutral axis is y bar. ಅಂದ್ರೆ ಅವಾಗ ಏನಾಗುತ್ತೆ, this area is multiplied by the distance of the centroid from the neutral axis. That is why that product is called as moment of the area. So moment of the area ಅಂದ್ರೆ area multiplied by distance of the centroid of that area from the neutral axis. That is called as a into y bar. So that means that integration whatever is there, that can be written as a into y bar. Now we have proved that the rate of change of bending moment with respect to distance gives the shear force. So in the last chapter, in BMD and SFD chapter, we have proved that dm by dx is f. ಅದನ್ನು ಪ್ರೂವ್ ಮಾಡಿದ್ವಿ ನಾವು. The relationship between bending moment, shear force and intensity of load, we have derived it. So dm by dx is f, that we have derived. F is the shear force, m is the bending moment. So ಅವಾಗ ಏನಾಗುತ್ತೆ, you can, in that place dm by dx you can put it as f. So q is equal to f divided by b into I into a into y bar. ಇದು ಫಾರ್ಮುಲಾ, ಇದು ಜ್ಞಾಪಕ ಇಟ್ಕೊಳ್ಬೇಕು. So here what you can see here is, here f is constant. Please note that shear force at a section at a particular section is constant. B also you will be knowing. B is the width of the section. I also you can calculate. Suppose if it is a rectangular section BDQ by 12, as you calculate ಮಾಡಬಹುದು. A into y bar is the only variable. So this A is nothing but the area of the section above this fiber. Suppose you illi tagondre at the neutral axis, what will be the what is the value of A? If you consider a layer here, area ಅಂದ್ರೆ ಇದ್ರ ಮೇಲೆ ಏನಿರುತ್ತೆ. Suppose if you take somewhere here, ಅದ್ರ ಮೇಲೆ ಏನು area ಇರುತ್ತೆ ಅದನ್ನ ತಗೊಳ್ಬೇಕು. So like that. I will explain that when I take up the problem. So area is A is the area above the strip. So this strip can be considered anywhere. ಈಗ ನಾನು ಇಲ್ಲಿ if I take y is equal to 0, if I take y is equal to 0, your strip will be here. Illirutte strip. Neutral axis itself is this strip. If y is equal to yt, your strip will be here. Top fiber iruttade. So like that. So y can vary from 0 to yt, or it can vary from 0 to yc also. Yc means yc ಅಂದ್ರೆ distance of compression fiber. Okay, ಇಲ್ಲಿಗೆ ಇರೋ ಡಿಸ್ಟೆನ್ಸ್ ತಗೊಂಡ್ರೆ ನೀವು ಅದನ್ನ ನೀವು ಸಾರಿ yb ಅಂದ್ರೆ ಬಾಟಮ್ ಫೈಬರ್. ಸೊ ಬಾಟಮ್ ಫೈಬರ್ ಅಂದ್ರೆ ಇದು, yt ಅಂದ್ರೆ ಟಾಪ್ ಫೈಬರ್, yb ಅಂದ್ರೆ ಬಾಟಮ್ ಫೈಬರ್. ಸೊ here for the derivation purpose we have considered an elemental strip above the neutral axis. That's all. Okay, now this is the formula you should remember for shear stress. ಯಾವುದು ಇದು, ಈ ಫಾರ್ಮುಲಾ ಕಲ್ತ್ಕೊಳ್ಬೇಕು. ಪ್ರಾಬ್ಲಮ್ ಮಾಡುವಾಗ ಇದನ್ನ ಯೂಸ್ ಮಾಡ್ತೀವಿ ನಾವು. Just like bending equation, this is called as your shear equation. So Q is equal to F divided by B into I into A into Y bar. Here F divided by B into I is constant in a given problem. A into Y bar will vary. So A and Y bar vary with distance Y. So Y change ಆಗ್ತಾ ಇದ್ದಾಗ Y bar ಮತ್ತೆ A change ಆಗ್ತಾ ಹೋಗುತ್ತೆ. That is the meaning. Now let us see how this can be how the variation of the shear stress across a standard section you can plot. ಅಂದ್ರೆ ಒಂದು ಸೆಕ್ಷನ್ ಅಲ್ಲಿ see here the section is a irregular section here shown, because this section can be triangle, rectangle or square or circular or I section or T section, ಯಾವ್ದು ಬೇಕಾದ್ರೂ ಆಗ್ಬೋದು ಆಯ್ತಾ. That is why he has given an arbitrary section like this. By if you vary the value of y, your shear stress also will vary. Even though shear force is constant, shear stress will vary at different depths. So ille shear stress ಬೇರೆ ಇರುತ್ತೆ, ille shear stress ಬೇರೆ ಇರುತ್ತೆ, ille shear stress ಬೇರೆ. Now let us see where the shear stress is maximum and where it is minimum, how it varies across the cross section. Just like bending stress ಯಾವ ರೀತಿ ವೇರಿ ಆಗುತ್ತೆ ನಿಮಗೆ ಲಾಸ್ಟ್ ಪ್ರಾಬ್ಲಮ್ ಒಂದು ಎಕ್ಸ್ಪ್ಲೈನ್ ಮಾಡಿದೆ. ಟಿ ಸೆಕ್ಷನ್ ಒಂದು ಪ್ರಾಬ್ಲಮ್ ಜಸ್ಟ್ ಶೋ ಯು. ಸೊ ಇದರಲ್ಲಿ ನೋಡಿ ಇಲ್ಲಿ ಇದು ಬೆಂಡಿಂಗ್ ಸ್ಟ್ರೆಸ್ ಡಯಾಗ್ರಾಮ್. ನೋಡಿ ಬೆಂಡಿಂಗ್ ಸ್ಟ್ರೆಸ್ ನ್ಯೂಟ್ರಲ್ ಆಕ್ಸಿಸ್ ನಲ್ಲಿ 0 ಇರುತ್ತೆ, ಹೋಗ್ತಾ ಹೋಗ್ತಾ ಜಾಸ್ತಿ ಆಗ್ತಾ ಹೋಗ್ತದೆ. ಇದು ಕಂಪ್ರೆಷನ್ ಇರುತ್ತೆ, ಇದು ಟೆನ್ಷನ್ ಇರುತ್ತೆ. ಸಿಂಪ್ಲಿ ಸಪೋರ್ಟೆಡ್ ಆದ್ರೆ ಕ್ಯಾಂಟಿಲಿವರ್ ಬೀಮ್ ಆದ್ರೆ ಇದು ಟೆನ್ಷನ್ ಇರ್ತದೆ, ಇದು ಕಂಪ್ರೆಷನ್ ಇರ್ತದೆ. ಸೊ ಇಟ್ ಇಸ್ ಲೀನಿಯರ್ ಸ್ಟ್ರೈಟ್ ಲೈನ್ ವೇರಿಯೇಷನ್. ಬೆಂಡಿಂಗ್ ಸ್ಟ್ರೆಸ್ ಇಸ್ ಎ straight line variation where you have bending stress at the neutral axis as 0 and it increases as you move towards the extreme fiber, whereas shear stress hagala adu parabola barutte because y square term barutte nimge. Let us see how we can get the expression for shear stress for standard cases, rectangular, circle matte triangle ಮೂರಕ್ಕೆ ಮಾಡಿದ್ದಾರೆ ಆಯ್ತಾ. So variation of shear stresses across standard sections. First, suppose if I take a rectangular section of a beam, how the shear stress varies across the depth. Adana find out ಮಾಡ್ಲಿಕ್ಕೆ ನೋಡಿ. For rectangular, this is how the derivation is important idu. So they may ask that shear stress derivation ಅಥವಾ ಇದನ್ನ ಕೇಳಬಹುದು. rectangle, circular, triangle ಮೂರಿದೆ, ಮೂರಲ್ಲಿ ಯಾವ್ದಾದ್ರು ಕೇಳಬಹುದು. So totally 4 derivations ಇದೆ. So you have to practice. So I am going to explain for rectangular. All of you observe here. So this is the rectangular section where B is the width, D is the depth. So neutral axis D by 2 ನಲ್ಲಿ ಇರ್ತದೆ, ಸೆಂಟರ್ ನಲ್ಲಿ ಇರ್ತದೆ. So neutral axis is also called as centroidal axis. So ಅದೇ ತರ ಮಾಡೋಣ ಈಗ. So this is the formula to find the shear stress. This is the formula, general formula. So F is the shear force at this section, B is the width of the section, I is moment of inertia of the section, A into Y bar is the moment of area of that moment of area above the layer with respect to neutral axis. That is A into Y bar. ನೋಡಿ ಅದನ್ನ ಇದಕ್ಕೆ ಅಪ್ಲೈ ಮಾಡಬೇಕಿದೆ. So we have to apply this formula to this rectangular section. So neutral axis center ನಲ್ಲಿ ಇರ್ತದೆ, exactly neutral centroidal axis. I will consider a strip here. AA ಇದೆಯಲ್ಲ ಇದೇ ಸ್ಟ್ರಿಪ್, ಅಲ್ಲಿ CD ಅಂತ ತಗೊಂಡಿದ್ದೀನಿ. Here we have taken it as AA. In the derivation it was CD, here it is AA. At a distance Y. See, Y is the distance from the neutral axis to that, B is the width. ಅರ್ಥ ಆಯ್ತಾ? ಈಗ ಎಕ್ಸ್ಪ್ರೆಷನ್ ಬರೆಯೋಣ. Q is equal to F by BI. So ಇಲ್ಲೇನಾಗುತ್ತೆ? See here. Q is equal to F by BI into A into Y bar. ಇದು ಫಾರ್ಮುಲಾ. ಈ ಫಾರ್ಮುಲಾ ಜ್ಞಾಪಕಟ್ಕೋಬೇಕು. So where AY bar is the moment of the area above the section about the neutral axis. ಈಗ ನೋಡೋಣ ಏರಿಯಾ ಏನಾಗುತ್ತೆ ಇಲ್ಲಿ. ಏರಿಯಾ ಅಂದ್ರೆ ಇದನ್ನ ತಗೊಳ್ಬೇಕು. A small a ಅಂದ್ರೆ ಯಾವುದು ಗೊತ್ತಾ? So from this layer up to the top fiber. So whatever area is there, shade ಮಾಡಿದಾರಲ್ಲ, the shaded region is the area. So ಇದರ ಪ್ರಕಾರ ಏರಿಯಾ ಏನಾಗುತ್ತೆ? ರೆಕ್ಟಾಂಗಲ್ ಬರುತ್ತೆ. So A is small a is equal to B into this. This is D by 2 minus Y. So that means your area is now B into D by 2 minus Y. Next, Y bar. Y bar is the distance of centroid of this area from the neutral axis. ಈ area the centroid. So area centroid ಇಲ್ಲಿರುತ್ತೆ centroid ಆಯ್ತಾ. ಸೊ ಅದು ನ್ಯೂಟ್ರಲ್ ಆಕ್ಸಿಸ್ ಇಂದ ಇಲ್ಲಿಂದ ಡಿಸ್ಟೆನ್ಸ್ ಇಲ್ಲಿ ಸೆಂಟ್ರಾಯ್ಡ್ ಗೆ ಎಷ್ಟಾಗುತ್ತೆ? y ಪ್ಲಸ್ ಇದೇನ್ ತಗೊಳ್ಬೇಕು? ಸೊ y ಪ್ಲಸ್ ಇಲ್ಲಿಂದ ಇಲ್ಲಿಗೆ ಈ ಡಿಸ್ಟೆನ್ಸ್ ಏನಿರುತ್ತೆ? d/2 ಮೈನಸ್ y ಇದೆ, ದಟ್ ಡಿವೈಡ್ ಬೈ 2 ತಗೋಬೇಕು. ಯಾಕಂದ್ರೆ ಇಲ್ಲಿರುತ್ತೆ ಸೆಂಟ್ರಾಯ್ಡ್ ಎಕ್ಸಾಕ್ಟ್ಲಿ ಅಟ್ ದಿ ಮಿಡ್ ಪಾಯಿಂಟ್ ಆಫ್ ರೆಕ್ಟಾಂಗಲ್. ಸೊ ಡಿಸ್ಟೆನ್ಸ್ y ಬಾರ್ ಅಂದ್ರೆ ಇಲ್ಲಿಂದ ಇಲ್ಲಿಗಿರೋ ಡಿಸ್ಟೆನ್ಸ್, ಅದನ್ನ ತೋರಿಸಿಲ್ಲ. ಯು ಕ್ಯಾನ್ ಮೇಕ್ ಎ ನೋಟ್ ಆಫ್ ದಟ್. So if you locate the centroid here, centroid of the shaded region, it will be here. So distance of the centroid from the neutral axis will be y plus d by 2 minus y is this whole divided by 2. So that is your see here. Y plus half of d by 2 minus y. So if you simplify that, you will get half into d by 2 plus y. So simplify ಮಾಡ್ಕೊಳ್ಳಿ ಅಷ್ಟೇ. So next A into y bar ಬೇಕು ನಮಗೆ ಈ ಫಾರ್ಮುಲಾ ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡಲಿಕ್ಕೆ. A ಇದು y bar ಇದು. ಓಕೆ, ಎರಡನ್ನು ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡಿ. A is b into d by 2 minus y into y bar is half into d by 2 plus y. If you simplify, a minus b into a plus b ಆಗುತ್ತೆ. So b by 4 into ನೋಡಿ ಏನಾಗುತ್ತೆ, ಸಿಂಪ್ಲಿಫೈ ಮಾಡ್ಕೊಳ್ಳಿ. So you will be getting, I think b by 2 ಬರುತ್ತಾ? 2 to cancel ಇಲ್ಲ. d square by 4 minus y square ಇದೆ, b by 4 ಆಗುತ್ತೆ ಅಂತ ಇದೆ. ಎಸ್, b by 4 ಆಗುತ್ತೆ. b by 2 ಅಂತ ಬಂದಿದೆ ಇಲ್ಲಿ. b by 2 ಸಿಂಪ್ಲಿಫೈ ಮಾಡಿ ಕರೆಕ್ಟ್ ಆಗಿ. ಇಲ್ಲೇನೋ ಮಿಸ್ಟೇಕ್ ಆಗಿದೆ ನೋಡಿ. ಇಲ್ಲಿ ಮಿಸ್ಟೇಕ್ ಆಗಿದೆ, ಇದು 2 ಬರಲ್ಲ, ಇಲ್ಲಿ ಪ್ರಿಂಟಿಂಗ್ ಮಿಸ್ಟೇಕ್ ಆಗಿದೆ. ಸೊ ಇದು b into d by 2 minus y ಇದೆ. ಸೊ this 2 is not there. Okay, into half of d by 2 plus y, then b by 2 into d square by 4 minus y square. I value bdq by 12. Rectangular section ಗೆ I value bdq by 12 ಅದು ಗೊತ್ತಿದೆ ನಮಗೆ ಫಾರ್ಮುಲಾ. ಸೊ ಇದ್ರ ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡ್ಬೇಕು ನಾವೀಗ. ಸೊ ನೋಡಿ ಇಲ್ಲಿ ay bar is this, ay bar is this, I is bdq by 12. ಈಗ ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡಿ. Therefore q is equal to f is constant, b is b only here. So width of the section b ನೇ ಇದೆ, I ಅಂದ್ರೆ ಇದು bdq by 12 into ay bar is this. So if you simplify ಮಾಡಿ, you will be getting like this, 6f divided by bdq into d square by 4 minus y square ಅಂತ ಬಂದಿದೆ. So this is the expression for shear stress across the section, across the depth. ಅಂದ್ರೆ by knowing the value of y, you can get the value of q at different values of y. ಇಲ್ಲಿ d constant, b constant, f constant, only y is the variable. Since you have got y square term here, so shear stress varies parabolically. So parabola manner ಅಲ್ಲಿ vary ಆಗುತ್ತೆ. ಯಾಕೆ? Because y square term is there. So that is the main difference. So bending stress linear distribution shear stress parabolic distribution. Shear stress curve parabola. ಈಗ ನೋಡಿ, by putting the values for y, you can get the values of q. So at y is equal to plus or minus d by 2 ಅಂದ್ರೆ ಏನು? What do you mean by plus or minus d by 2? So plus d by 2 means if the y is measured above the neutral axis, it is plus. If it is y is measured below the neutral axis, it is minus. So plus d by 2 means ಇದು plus d by 2, ಇದು minus d by 2. Okay. So if you put y is equal to plus or minus d by 2, what is the value of q there? So q becomes 0 here. See here. If you put y is equal to plus or minus d by 2, so y square ಏನಾಗುತ್ತೆ? d square by 4 ಆಗುತ್ತೆ. So ಅವಾಗ ಇದು plus or minus ಸ್ಕ್ವೇರ್ ಇರೋದ್ರಿಂದ ಪ್ಲಸ್ ಆಗುತ್ತೆ. So cancel ಆಗುತ್ತೆ. So it becomes 0. So q becomes 0. That means at the farthest fiber, shear stress is 0. ಮೇಲ್ಗಡೆ ಕೆಳಗಡೆ ಎರಡು ಕಡೆನೂ 0 ಇರುತ್ತೆ. What is the value of shear stress at y is equal to 0? So y is equal to 0 means at neutral axis. Y is equal to 0 on the neutral axis nani 0 irutade. Because y is measured from neutral axis, y is equal to 0 means here, illi. So alli shear stress enirutte? If you put y is equal to 0 in this expression, what you will get? You will get 6f by bd cube into d square by 4 anta barutte. Y 0 agutade. Sarina? That can be written as 6 by 4 is 1.5 into f divided by bd. What is this f divided by bd? So f is the shear force, b into d is the area over which the shear force is acting. So it is called as average shear stress. So shear force divided by area is called as the average or mean shear stress. Mean shear stress or average shear stress over the entire area. So actually, strictly speaking, shear stress varies from point to point across the depth. So then how to get the average shear stress? Average shear stress is given by shear force divided by area of that section. That's the average. So illi maximum barutte. Illi maximum irutte. Hogta 0 agtade. Variation parabola. So at the neutral axis, shear stress is, you can prove that it is 1.5 times the average shear stress. So it is very important book work. Show that in the case of a rectangular cross section of a beam, maximum shear stress is 1.5 times the average shear stress, and it occurs at the neutral axis. So now the difference very important. Bending stress neutral axis is 0 irutte. So the neutral axis ide rectangular section ge, for the same rectangular section, if you plot the bending stress distribution, ಅದೇನಂತೆ ಗೊತ್ತಾ? ಇಲ್ಲಿ ವರ್ಟಿಕಲ್ ಲೈನ್ ಬರುತ್ತೆ, ಹೀಗೆ ಬರುತ್ತೆ. ಸೊ ಇಲ್ಲಿ ಮೇಲ್ಗಡೆ ಕಂಪ್ರೆಷನ್, ಕೆಳಗಡೆ ಟೆನ್ಷನ್ ಇರುತ್ತೆ. ಆದ್ರೆ ಇಲ್ಲಿ ಅಂದ್ರೆ ನ್ಯೂಟ್ರಲ್ ಆಕ್ಸಿಸ್ ಅಲ್ಲಿ ಬೆಂಡಿಂಗ್ ಸ್ಟ್ರೆಸ್ 0, ಬಟ್ ಶಿಯರ್ ಸ್ಟ್ರೆಸ್ ಮ್ಯಾಕ್ಸಿಮಮ್. ನೆನಪಿಟ್ಕೋಬೇಕು. ಸೊ ನ್ಯೂಟ್ರಲ್ ಅಟ್ ದಿ ನ್ಯೂಟ್ರಲ್ ಆಕ್ಸಿಸ್ ಇನ್ ದಿಸ್ ಕೇಸ್, in the case of rectangle, ಎಲ್ಲದರಲ್ಲೂ ಅಲ್ಲ, in the case of rectangular section, you have maximum shear stress at the neutral axis and 0 bending stress at the neutral axis. And bending stress increases when you move away from the neutral axis. So extreme fiber alli bending stress maximum irutte, whereas extreme fiber alli shear stress 0 irutte. Not 0 irutte. And the variation is parabola. Idana smooth curve tara join. So by plotting this diagram, so this diagram is called as shear stress distribution diagram. Idana shear stress distribution diagram antivi. So idu parabola irutte, whereas problem ಎರಡು ಕೇಳಬಹುದು. They may ask you to draw both bending stress as well as shear stress distribution for a type of problem. Rectangle ಆಗ್ಬೋದು, I section, T section, ಯಾವ್ದಾದ್ರು ಆಗ್ಬೋದು. They may ask you to plot the bending stress and the shear stress distribution. ನಿಮಗೆ T section I have shown bending stress distribution. So ಅದೇ ತರ ಅದೇ T section ಗೆ shear stress distribution they may ask. That will take up problem ಮಾಡೋಕೆ ಹೇಳ್ತೀನಿ. So now in this book work, what we explained was the maximum shear stress in a rectangular section is 1.5 times the average shear stress anta we have proved. Okay. Many of you are absent today. I think I have to call them. I don't know what is the reason. I had to give some assignment for them, additional assignment, those who are absent. Yes, now this is the derivation for rectangular section. Now, similarly, you have the derivation for circular section. So, circular section, I don't want to explain. You just go through this. It is done in this manner using trigonometrical relations. I want you to study that. Anyway, triangular I will explain. One more is there. There are three book ones. Circular, I want you to explain. In the case of circular section, your maximum shear stress will be 4 by 3 times, that is 1.33 times the average shear stress. You can prove that. Proof has been done there. Now, the triangular section you will consider isosceles triangle. So, in the case of isosceles triangular section, so B is the width of the triangle, H is the height of the triangle, or the depth of the triangle, total. So, now here we will take, now in this case, this is a little bit different I have done. Y is measured from the top here, not from the neutral axis. Actually, neutral axis will be here. This is the centroid of this triangular section. So you know that centroid of a triangular section will be at h by 3 from the base or 2h by 3 from the vertex. This is the vertex, this is the base. So this is G is the capital G is the centroid of this triangle. Now we will consider an elemental strip at a depth y, at a depth y from the vertex. This is the vertex or the apex. And you shade this area above this whatever area is there, you shade that. So that area is small a. So in this case, small a is this area. Okay. Then 2y by 3 is the distance of centroid. Small g is the centroid of the shaded area. So triangle shaded area. 2y by 3 is the distance from the apex to the small g. Okay. So this is the diagram. This is the section of the beam. B dash is the width of this elemental strip. This width is B dash. So you can get a relationship between this B dash and B. So by similar triangle principle, so you can see that this triangle and this triangle, they are similar. So you can take the respective sides are proportional to each other. To y divided by h. Similar triangle principle. B dash divided by B will be y divided by h. So from that you can get the value of B dash. So now let us plot the shear stress distribution for this triangular section. So as I already told, so this is from similar triangle. So B dash by B is equal to y divided by h, means B dash will be y by h into B. So now let us calculate the area above this AA. So this is your AA. Please note that this is your AA. Area above this will be half into B dash into Y. Okay? Half into B dash into Y. That is the area. Small a is that area. See here. Now substitute for B dash. B dash is Y by B into Y by H into B. So that's what they have substituted here. And then it becomes y square. Y into y becomes y square. So this is the expression for A. Then centroid, as I already told, centroid of this shaded area will be at a distance of 2y by 3 from the apex, from the vertex. Now I want y bar. So what is y bar in that formula? Y bar is the distance of this centroid G, small g, from the neutral axis. Neutral axis is here. Please note that this is the neutral axis where the centroid of the triangle is there. The axis passing through that centroid or the new centroidal axis itself is called as the neutral axis. So from here to here, so this distance is your y bar, distance between capital G and small g. So distance of the centroid of this shaded area from the neutral axis is y bar. Now let us see what is y bar. So from the diagram, we can get the distance between capital G and small g. So what is that? It is distance of shaded area, centroid of shaded area above the section AA from the neutral axis. Y bar is 2h by 3 minus 2y by 3. See that. So this distance I need. So this distance will be this total distance 2h by 3 minus this distance, okay, 2y by 3. That's correct. 2h by 3 minus 2y by 3 is the y bar distance. Now you can substitute in that formula. So a into y bar. So a is this half into b by h into y square. Y bar is this, multiply that. So a into y bar and simplify, you will get this. Now moment of inertia of triangular section about the neutral axis. Neutral axis means centroidal axis. You know that it is bh cube by 36, standard formula. You should remember that. Moment of inertia of this triangular section about this centroidal axis or the neutral axis is bh cube by 36, standard formula. About the base it is bh cube by 12. About the centroidal axis it is bh cube by 36. So that I value you have to use bh cube by 36. Now you can substitute in that formula. What is that formula? You have got q is equal to f by vi into a into y bar. So what is f? F is the shear force which is constant, divided by b is b dash shear. Please note that. We are calculating the shear stress here at this level. So at this level width is b dash. So instead of b we have to take b dash because we are calculating at that elemental strip level. So b dash is y by h into b, that they have substituted, into bh cube by 36 the I value, into a into y bar we have just calculated here. So a into y bar is this. So this you substitute, and if you simplify the entire thing, you will be getting an expression like this: 12f by bh cube into y into h minus y. After simplification, you are going to get this. Now let us put the values of y. So y is measured from the apex, from the vertex. If y is equal to 0 means y is measured from here. Please note. In this derivation, y is measured from the top. So if y is 0, that is at this point. And if y is equal to h, that is at this point. Let us calculate y is equal to 0 and y is equal to h, the value of q. At y is equal to 0 and y is equal to h. See, we have got this expression for q. Now put y is equal to 0 in this. If you put y is equal to 0, q becomes 0. If you put y is equal to h also, q becomes 0. That means you have got the value of shear stress at top and bottom fiber as 0, 0. See here, 0, 0. Now at the centroid means here, neutral axis. At the neutral axis here, at this point, what is the shear stress? Let us calculate. So if you want at the centroid, you have to put y is equal to 2h by 3. If you put y is equal to 2h by 3, you will get the shear stress here. So q is equal to, put y is equal to 2h by 3 and simplify. So you will simplify. So in this, put y is equal to 2h by 3. So y is 2h by 3, h minus 2h by 3. And if you simplify that, you will be getting like this: 4 by 3 into f divided by half bh, or f divided by bh, 8 by 3 into f divided by bh you are getting. So this I will write it as 4 by 3 into f divided by half bh. So this 8 can be written as 4 divided by half. Why it is written like this is, this half bh is nothing but the area of the triangle. So area of the triangular section. So shear force is f. Half bh is the area. So shear force divided by area gives the shear stress, that is the average shear stress. So average shear stress is always f divided by the area of the section. Here area of the triangular section is half bh, half base into height. So therefore you got 4 by 3 into q average or mean shear stress. So now here what you can say here is, in the case of a triangular, isosceles triangular section, q at the level of neutral axis, shear stress at the level of neutral axis is 4 by 3 times the average shear stress. So see here, it is plotted. Q at the centroid is 4 by 3 times average shear stress. Now we don't know where the maximum shear stress occurs. It is not occurring at the neutral axis level. Let us see where the maximum shear stress occurs. In this case, maximum shear stress occurs at some other distance. Let us calculate that. To calculate maximum shear stress, the condition is dq by dy is equal to 0. So because the condition for minimum and maximum of a function is its first derivative should be 0. That you have learned in mathematics, differential calculus. So for q max, dq by dy is equal to 0. Now what you have to do is, this is the expression for q. Differentiate this with respect to y and equate it to 0. So when you are differentiating it, 12f divided by bh cube is a constant. Okay, that's a constant into yh minus y square. You are getting like that. So yh minus y square means if you differentiate that with respect to y, you are getting h minus 2y. So once you differentiate that, you will be getting like this. See here, 12f minus bh cube is a constant, h minus 2y is the differentiation, is equal to 0 again. So this cannot be 0, therefore the condition is h minus 2y is equal to 0 or y is equal to h by 2. That means what you can say here is, when y is equal to h by 2, you have the maximum shear stress value. So what is its value then? So its value is, put y is equal to h by 2 in this expression. Put y is equal to h by 2 in this. So now we got to know where the maximum shear stress occurs. So maximum shear stress occurs at y is equal to h by 2. So put y is equal to h by 2 in this expression for shear stress. So put here in the place of y h by 2, in the place of h by 2, and you simplify, you will get, see here, you will get, put y is equal to h by 2, you will get this. So if you simplify this, you are getting 3f by bh. Once again, I want to express this in terms of average shear stress. To express this in terms of average shear stress, denominator should be half bh, which is the area. So if you want denominator of bh, so 1.5 divided by half is 3. So it is divided like this. Half bh is the area. F is the shear force. Shear force divided by area gives the shear stress, average shear stress. So 1.5 times Q average you are going to get. So that means in the case of isosceles triangular section, it's a particular special case where you have maximum shear stress at y is equal to h by 2. Maximum shear stress is at y is equal to h by 2, and at neutral axis shear stress value is 4 by 3 times average. Maximum shear stress is 1.5 times Q average, and at the neutral axis shear stress is 1.33 times average shear stress. So this is the derivation for shear stress distribution in a isosceles triangle section of a beam. So I explained you rectangular and triangular. So circular has been done in the there. You try to understand that circular cross section. So some trigonometrical conversions are there. You try to understand that. That is also important. You just go through that. So all the things I cannot cover. So you have to try on your own. So this is a subject where your effort is most required. So many problems I have been explaining. Derivations, the shear stress derivation we did, rectangular and triangular I explained. You can try to work it out that circular. When you see to that circular cross section, if you have any difficulty, you can call me and you can ask me. Okay. So it's a very neatly he has explained in this. Circular also has neatly explained. All the diagrams are very clear, so you can just understand once you practice. Some integrations are required. That's all. Nothing else. Limits of integration has to be understood. So now I think I will stop here. Next problems I am going to take up on T section, I section, like that. So then this bending stress and shear stress will be over. Then I had to take up torsion. So torsion also is there in the fourth module only. So if I complete the shear stress, then only 50% of module 4 is over. Another 50% is torsion of shafts that I have to cover. So these are all the strength parameters of materials. So we have studied about tension, compression, shear and bending. So 4 types are covered. Then we have to go to torsion. So these are all the different topics you should be thorough. So whatever assignments I have given, I think I have given in assignments in second module and third module, second assignment. BMD, SFD, compound stress and thick and thin cylinders I have given. So you have to practice. I have given only some 8 to 10 problems, 8 problems I think. But you have to practice more number of problems. Then only you will be confident. Otherwise, very difficult to because this online class. So whatever maximum possible, I am explaining. But from your side also, you have to work. Okay. So next class I will be discussing about I section, T section problems on shear stress on these things. So I think another one class I can complete this shear stress, 1 or 2 classes. Then I will take up torsion. So for the test MSc 2, the IA2 internal assessment 2, you have up to shear stress. So anyway, even if I start torsion, that will not be there for you for the IA2. I will be taking that in the IA3. So for the IA2, portions will be thick and thin cylinders. From module 2, thin cylinder and thick cylinder I am giving. Then complete BMD and SFD, module 3 complete. Then module 4, bending system shear stress. So up to these the topics you have to study for your internal assessment too. So just like the pattern will be same, 3 questions compulsory. In 2 questions you will be having internal choice, similar to your first internal assessment.
Sir?
Yes.
What in 4th module, sir? That was not quite audible.
Yes, yes.
What is the topic in 4th module for second IA?
This is 4th module, what I am doing now. Bending stress and shear stress.
Thank you, sir.
That is in 4th module. Torsion also is there in 4th module, but I am not giving problems from torsion for the test. I will be giving in 3rd test. Okay. So second test portions, module 2, thin cylinder, thick cylinder. Module 3, bending moment and shear force complete. Module 3 complete. Then module 4, bending stress and shear stress. So problems on the derivation you have to go through. Okay. I'll take the attendance, but unless you practice, it's very difficult. And keep on telling this subject and fluid mechanics, you should be very careful. Both are problematic subjects, and you need to work a lot. Yes. 1827. 1827.
Present, sir.
19001.
Present, sir.
003.
Yes, sir.
005.
Present, sir.
6.
Present, sir.
7.
Present, sir.
10.
Present, sir.
12.
Present, sir.
13.
Present, sir.
18. 18. 19.
Present, sir.
21.
Yes, sir. Sir, 18.
Yes.
Sir, 18.
18. Okay.
CV 18.
18, 28. Not there. 18,
Sir,
27.
16 present, sir.
Sir, 18
16. Okay. 16 present.
Sir, 18
Yes,
present.
sir. Network problem ಅಂತ.
16 ಕಾಣಿಸ್ತಾನೆ ಇಲ್ವಲ್ಲ ಇಲ್ಲಿ ನಂಬರ್.
Sir, connectivity
Sir,
problem.
ಇದ್ರು ಸರ್ ಈಗ ಲಾಗ್ ಔಟ್ ಆಗಿದೆ.
Yes, sir.
ಓ ನಿಮ್ದು ವಾಯ್ಸ್ ಕೇಳಿಸ್ತಾ ಇದೆ. ಇಲ್ಲಿ ನಂಬರ್ ತೋರಿಸ್ತಾ ಇಲ್ಲ.
ಸರ್ ಅದು
ಏನು
ಕನೆಕ್ಟಿವಿಟಿ ಪ್ರಾಬ್ಲಮ್ ಇತ್ತಂತೆ ಸರ್, ಅದಕ್ಕೆ ಲಾಗೌಟ್ ಆಗಿದೆ.
ನಿಮ್ಮ ಹೆಸರೇನು ಹೇಳಿ? 16
ಶ್ರೀಲಕ್ಷ್ಮಿ ಅಂತ ಸರ್ ಅವಳದು.
ನೀವೇ ಅಲ್ಲ ಡೌಟ್ ಕೇಳಿದ್ದ? ಹಾ, ಓಕೆ. ಸೊ ಪ್ರಾಕ್ಟೀಸ್ ದಿ ಪ್ರಾಬ್ಲಮ್ಸ್. ಸರ್ಕ್ಯುಲರ್ ಸೆಕ್ಷನ್ ಒಂದು ಅರ್ಥ ಮಾಡ್ಕೊಳ್ಳಿ, ಟ್ರೈ ಮಾಡಿ. ಡೌಟ್ ಇದ್ರೆ ಮತ್ತೆ ಹೇಳ್ಕೊಡ್ತೇನೆ. ಓಕೆ, ವಿಲ್ ಮೀಟ್ ಇನ್ ನೆಕ್ಸ್ಟ್ ಕ್ಲಾಸ್.